I want to kind of go back to this picture because I had briefly shown this picture, but I hadn't really said much about it and why I showed so many systems together. Um, Basically, these are examples of systems where the nonlinearity reigns pretty supreme. And there are not that many uh, of these systems that are really known to us, which are relatively simple and transparent and can be tracked in great detail, uh, depending upon the boundary conditions imposed, depending upon the initial conditions used, and so on. So these three systems, the Hertz, the Fermi, Pasta-Ulam, Singo, and what one can imagine as the electron chain, these are very fundamental systems, and they have their analogs. They have their twins, digital twins. They have their real twins in other areas also. So therefore, these are some of the very interesting, not completely understood and known. Many phenomena are being observed for the first time every now and then, even now, kind of systems. Now, we have spent a little bit of time on the Fermi-Pasta-Ulam system, and I have also introduced the Hertz system, and that's what we are studying. And this is kind of what we will finish up with for the most part. I don't have a plan to go into this system, but let me explain to you this system because while I don't have a plan to show you the results and all that, I can still show you quite a bit. Of course, I have also done the Toda system, and there's a particular system that Vivek has been playing with. Toda system we can solve, and so because it's an integrable system, I've avoided it. But I should point out that the Toda system also has extremely complicated physics, and that is surprising to me. Okay, Toda problem was solved in what, 1967, I think. So, uh, almost 60 years later, there are plots that we are making of the Toda system that are mind-boggling. And actually, I can show you one of them just to show you how mind-boggling these plots are. Give me a second, because this is stuff I'm looking at right now. So let me share the screen. I think I can. Um, okay. So if you look at this plot, can you see this plot? Okay. So here you see it's a Toda chain, but a velocity perturbation is being given around particle 10. And this makes a soliton, which is an integrable soliton. We know it's a set square function, comes back and bounces back and forth. But as it does so, and as this perturbation is initiated, see all these other oscillations that are also forming. And these oscillations basically are tails of the soliton. So there's like a soliton pulse. And after the soliton pulse, let's say, goes by this way to the right, there is a tail that you will feel. And that tail is not very big. It's many orders of magnitude smaller even. But it is a real tail. It's not an error. And all this junk that you're seeing are tail effects. They are background effects. We don't know what happens in late times. Whether the tail stabilizes to background oscillations and kind of that's that, or whether the tail continues to grow and overpowers the soliton, we don't know that. So this is an example of something that's completely unknown in a Toda system which is solvable. Here we have hard boundaries at the two ends, and the z-axis scale is logarithmic. So what that means is that the small effects are vastly amplified such that we can see them. Now let me show you another one of these, which is same kind of stuff, but let me see how can I, okay. So this is another close-up picture, same thing, another angle. And here you see around particle 10, the soliton is there, it reflects back. But then you see the tail effects. Again, on a logarithmic scale, it goes by 10 orders of magnitude. So therefore, there are vastly different scales involved. But you can see that there is clear-cut evidence of these waves traveling through this reflected soliton, and as a consequence, presumably having some forms of change. How much change, what change at this scale, it is not easy to say. It is not even easy to say whether they pass through each other unscathed, but it is anybody's guess as to what is going on. Clearly, the system has high levels of complexity and complication. So we actually, to be very honest, we still have very limited knowledge of these systems. Now, add to what I said, the fact that this solution is technically, analytically known, but it is not very useful. Because if you have many infinite sums of many analytical functions, at the end of the day, it's not all that closed form at all, which means that you are end with having to struggle with how to describe it. Here we have done just very accurate simulations, but you can see, there's very complicated physics in this problem. So coming back, let me go back to the PowerPoint. So coming back, you can kind of see that even the Toda chain, which I haven't bothered to put in here, is extremely complex. So therefore, these guys are obviously also very, very complex. So anyways, we are talking Hertz. We have done some Fermi-Pascal-Olam. We might do a little bit more today, but we haven't done this magnet system or the electron chain. The electron chain is a fascinating problem, and this is not a problem that I invented by any means. People have looked into this problem experimentally, but experimentally this problem is difficult to do because the way it is done is by using magnets and attaching the magnets with springs. And you can see that one way of doing this is by making the like poles face each other. So let's say this is the South Pole and South Pole face each other, which means they repel. Similarly, North Pole and North Pole face it, which means they repel. So in other words, it's a strongly repulsive system. Now, there are magnets which are very cheap and they're very strong. And one example of that is neodymium. You can buy neodymium magnets online. The problem is that once they get stuck to each other, you've had it because the magnetic force is extremely strong. In fact, there's a funny thing happened. A friend of mine who's a mechanical engineering professor, he wanted to run an experiment of this magnet chain in his basement. Well, he got the neodymium magnets. He was running the experiment when something went wrong with the alignment of the system. And then he had these neodymium magnets not only stuck all over themselves, impossible to separate almost, They also got stuck to various columns and pillars in his basement. So he just flew. They're extremely strong. And Tony told me that it was a nightmare to play with them. I'm never going to touch them again. So they're not easy to deal with. Anyway, but the good thing is that mechanical engineers also have invented these magnet shoes, if you will. So it's like a device like this, like my cell phone here, with a groove here. And the magnet fits into that groove. And then you place these devices one after the other along a track. So it becomes approximately this system. So it is experimentally realizable, accepting it is not easy to do, but it's much easier to do than what Tony was trying, which was a little bit more cavalier than this more tame way. Anyway, this is a highly, highly repulsive system. Therefore, you have to bound it at the end walls, otherwise they'll just run away to infinity. But the thing is, if you perturb this system, the system is so sensitive that to the extent we can tell, the perturbation never stops unless friction kills it. Okay, so is this an integrable system? Short answer is I'm not sure. The long answer is most likely yes. There is a system that is integrable that's very similar to this, probably the same as this. But even though it's integrable, the solution is not simple. And it's called, let me see if I can type it up. I do believe that that's the same system as this. It's called the Calogero-Sutherland system. And the Calogero-Sutherland system has been worked on in the classical and quantum domains by obviously Sutherland and Calogero and several other people. Now, this system tries to take what we have done here and generalizes that a little bit. In most of my studies, I've turned off the springs because the repulsion is very good. If you turn on the springs, it just is a little bit more bouncier. But I thought about this system as a way in which one might be able to make a wind energy driven device. So a wind to electrical energy conversion device. The idea is that if you have alignments like this on your roof, any wind blows, and if the wind can get inside the system, you can immediately see it'll make the system go. And then you put solenoid around it and you take the current out. As simple as that. Of course, that it's lossy, but all induction processes are lossy. So nobody has done the experiment, but I have certainly proposed it. Now, coming back, this system is very interesting. It's probably an integrable system, a Calogero-Sutherland type system, maybe the same system almost. Details aside, I think roughly. Anyway, so let me now go back to the Hertz problem. Let me point out that all of these three problems are also extremely complex, just like the other problem. And I showed you this, that if Nesterenko tried to go to the Hertz problem under strong loading conditions, that would basically mean in this equation here, delta is larger than this piece, the bond stretch or squeeze piece. If delta is more, be sure that a KdV problem should come about. Now, I haven't seen the KdV problem come about in our simulations. He also showed that if delta is small compared to this bond stretch, then you get a highly nonlinear equation, which is Nesterenko's equation, which is this equation. And he showed that, well, this cannot be solved, but with some kind of twists and turns, by simplifying it, you can show that a solitron solution is consistent. Now, I had problems with both of Nesterenko's problems, this problem and that problem, because the solutions we find for this problem is not the same as what Nesterenko gets, but they are pretty close. So if you are an engineer as opposed to a physicist, you would say this is fine. But since I am not an engineer, it bugs me. Okay. What is the difference? If you have 10% error in a problem, engineer says that's fine. If you have 1% or half percent error in a problem, physicist is typically fussing. So that's the difference between Vitaly and me. Anyway, the fact that this KDV solution that Vitaly proposed is something we never found had been on my mind and bothering me for a long time. So I'll tell you what happens there. Anyway, if you do a very high quality simulation, you start a perturbation, you'll basically find a solitary wave that's moving around. Now, I've already told you that the solitary waves have a certain width. The width is proportional to the Hertz law, and Hertz law in this case has this 5/2 power for the potential. So the width is tied to this 5/2 power. If this 5/2 power goes to infinity, the width goes to 1. If this 5/2 power goes to 2, width goes to infinity. Because there is no solitary wave if you have a harmonic system. And I also pointed out that this power rigorously goes to 2 if instead of taking spheres, you take disks. In other words, as you go from 3D to 2D, this goes to harmonic and no solitrons in harmonic. All right. So just to summarize then, Nesterenko's equations are there. This is one of the, one of those 3 or 4 very interesting problems. You have solitary waves. The solitary wave width is tied to this power, which I showed you here. As you vary the power, the width goes from very tight to quite floppy and long and eventually to infinity. Now, I also showed you the experiment, and I showed you the form that this wave takes depending upon delta, the loading part. If there is no loading, there is a beautiful solitary wave. If there is tiny loading, you have a solitary wave followed by a flat region here, a flat region, and a tail. And then as you raise the loading, the flat region here shrinks, and eventually they merge, and eventually it becomes very much like an acoustic wave. Now, is it an acoustic wave? If you want to be very careful, the answer is no. Why not? Because you see, when you look at our equation here, the reason why that wave comes is because of loading. That's exactly what we are varying, because of loading. So if you have some loading, let's say you take the loading part, let's say you take this part. You take this part outside, and you expand the inside in powers of delta. You will get quadratic term. So you will get a harmonic term. Quadratic will be harmonic. Actually, in this case, linear would be harmonic. You'll get a linear term. Then you'll get a square term. Then you'll get a cubic term. Then you'll get a 4th order term. Blah, 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 blah. So what happens is that moment you do a Taylor expansion of these quantities which are being raised to some power, this Taylor expansion is going to give you all powers along with a linear power. Linear power may be dominant, but even then, the nonlinear powers are not to be forgotten. We already know in Fermi-Pasta-Ulam-Singhou system, a weak nonlinearity changes the problem big time. We have seen that. We have studied that. So therefore, my thinking is that just because you have loading, even if the loading is quite a bit, which is 1,000th of the diameter, this guy may look like a harmonic wave, but it's not. Because it is impossible to differentiate between a harmonic and a nonlinear wave beyond a point. I mean, here, for example, you can see in a harmonic wave, we already discussed from Kathia's solution, it's a Bessel function. Here you can see how uneven this is. See, there are beating type effects coming in. So actually, one would be hard pressed to say that this is a harmonic wave. So these systems are very complicated, and these solutions, therefore, are naturally very difficult analytically to do. I told you about how the waves cross, and I told you that if we look at it carefully, you have the secondary wave formation, which are same in size because that's controlled by the potential, if you recall. But they're very tiny. They're many orders of magnitude less. And this particular problem is basically the equivalent of a hard wall collision because this mass doesn't move. It has no kinetic energy. So it behaves like an infinite mass. Bottom line is that you therefore have a situation where you have this secondary wave formation, which has its implications, as we discussed. And then I showed you this very important experiment. This is, by the way, an experiment. This is the part that is the simulation and the estimate. That's this part. But these B and C are actually experiment and let's see. B is force measurements and C is the simulation. So this is the simulation in C. This is the experiment in B. Now, again, the data containing these three peaks is from the sensor in the bead, okay? And the data containing the center peaks is from the sensor at the end. So you can see that in this experiment, they're picking up this wave, which is going from left to right, this wave, which is after reflection, going from right to left. It's not a reflection, it's a backscattering. Reflection is too simple for it. And then it has this secondary wave, baby wave, same size, same everything, much less amplitude. But this is about a third or fourth of this wave. And I told you that this was a very exciting thing for me to experience because I had predicted that with my student at the time. But I had no hope of it ever being seen because the effect seemed extremely tiny. And then this experiment comes along and says if you take a soft wall, the effect is much larger, and therefore what you had predicted can be seen. And that was the subject of this paper, unbelievably long time ago. So this I've already shown you. I just added this explanation. So then came the following logic. The logic is that if the solitary waves hit a wall and break down, how long can the process continue? So if every time a wave hits a wall, it breaks down, or wave hits each other, it breaks down, then before you know it, all the energy will be gone. That doesn't make sense because you have energy conservation. So the idea is that as there is a breakdown process, there has to also be a growth process. And the growth processes are these. In one case, a more energetic wave, which is a big wave, and the small wave are traveling together, and the big wave comes from behind and overtakes a small wave. When this phenomena happens, the big wave becomes bigger, and the small wave becomes smaller. It's like the rich getting richer, right? It's the rich getting richer. And if there is a collision between the rich and the poor, head on, not overtaking. This is overtaking. both moving in same direction. This is head on between rich and poor. Then guess what? The poor wins. So in this case, the small wave goes in head on collision. The poor wins. So there are these two growth processes happening. So now you can see that the energy decimation process to make small waves and the energy capture process to make big waves, once these two processes begin to balance each other, the system should reach some kind of a steady state. And of course, initially some particles carried the energy as a function of time, and at later time, everybody would carry the energy, just like some kind of equipartition should happen. So even a purely nonlinear system, nothing to do with statistical mechanics and temperature, is headed towards a thermal equilibrium of some kind. Not quite thermal, but thermal-like. And this was a plot, one of the last plots I think I had discussed, where we do something very simple. We take the entire system, we observe it at various points in time for many time instants, and we just go and pick out the fastest moving particle at a given point in time. Because this is a nonlinear wave, the wave energy determines the wave speed. Larger waves travel faster. Smaller waves travel slower. This is a hallmark of nonlinearity. In nonlinear waves, this is what happens. So all we are doing is we are tracking the fastest moving wave, which means we are tracking the largest solitary wave-like structure. That's what this Vmax measures. And as you can see, the system after about t equal to 3 or so stabilizes. Although it has formidable fluctuations, large fluctuations, it stabilizes. So then came the question that if you let the system evolve and if you want to visualize it, what happens? What do you see? And then came this particular result. I think it's a very remarkable result. We published it in somewhere, PhysRev, I think. But the result means the following. This is a 25 particle system. And here we are observing it in time. It's a large amount of time. This is microsecond. Our time unit is fractions of nanoseconds, actually, or 1/100th of a nanosecond type time unit. Anyway, we start a velocity perturbation here. That creates a solitary wave. Again, it's a Hertz chain. And solitary wave, every time it hits a wall, comes back, it breaks down. And if you look at it carefully, even with this relatively low resolution, you will clearly see that this big wave is slowly getting washed off and getting dispersed into these large fluctuation and low fluctuation regions. Fluctuation in kinetic energy. The grayscale here, the dark entity here is actually kinetic energy. So kinetic energy of every particle as a function of time is being captured. So it's really a three-dimensional plot you're looking from above. And if the system were to go to equilibrium, naively we can imagine that then it would become a perfectly grayscale, because equilibrium would mean that everybody on average has the same amount of energy, so equipartition is followed and so on and so forth, which means that basically you'll go to a grayscale. Now, even after going that deep in time, we find that the system ends up in this very patchy scale state, very patchy. Big blobs of black, then blobs of white and all that. Something in between, no uniformity in gray at all. By the way, this is for n equal to 2.1. This is the power law in the potential, which means that the solitary wave is wide. This is n equal to 2.5, which means the solitary wave is 5 grains wide. Here it's more than that. And now you see, as you make n bigger, the solitary wave becomes tighter. And as it becomes tighter, meaning smaller, the dispersion slows down. So here you can see the solitary wave, and here you cannot. It's gone. It's broken down a lot. Why? Because the bigger wave is more prone to interaction with other waves because of its size. System size is the same. So this one has gone more towards the grayscale than this lower one. This guy also is the same thing as the top one, excepting here you have an even number of grains, here you have an odd number of grains. And same is repeated here. The effect is by and large the same, but you can see that even and odd are not exactly the same. The dynamics is a little bit different. So the number of particles does matter in this problem. All right. So this state, this kind of a fluctuating grayscale state, same as this state here, is what we decided to call quasi-equilibrium state. Because we were pretty sure it is not equilibrium, but it was an extremely stable state. We couldn't get out of it. In fact, it took us quite a few years to get out of it and go to real equilibrium. So when we reached this point where you see these plots, this was around 2000. This was first published in 2004, but this was published in 2011. We're carrying on with the work. And at that point, it became pretty obvious to me that the system is not going to true equilibrium or equipartition, where every particle on average will have the same kinetic energy or same energy. So how do we know then that how does a system go to equilibrium? We have to have a way of measuring how a system is going to go to equilibrium. So after some head scratching, it occurred to me that why don't I think about the virial theorem? So you all have learned virial theorem in mechanics, I'm sure, but let me go over it. So what is the virial theorem? The virial theorem is among the most underrated theorems for us physicists. The virial theorem turns out to be quite a bread and butter item for the astrophysicist. But the point about the virial theorem is, I'll give you the sort of punchline. The point is, the virial theorem tells you that in a given system, how much of the energy is kinetic, how much of the energy is potential, when the system has reached a fairly stable state of evolution. How much is kinetic, how much is potential. Very important information, right? You have a system, very complex system. Let's say you have like a DNA system, and you want to find out how much kinetic energy the DNA carries. You know the total energy, you know the potential energy too because of virial theorem. Very important. Anyway, the virial theorem takes a funny quantity. You see, if it were R cross P, that would have been a torque, right? So instead of having a cross product, it's a dot product of R and P. And that is this quantity G. So you have a system of n particles, so Pi dot Ri summed over all I. That's your G. G is a scalar. And then you take the time derivative of G, dg dt, and then dg dt is of course Ri dot Pi plus Pi dot Ri. Ri dot is same as velocity, obviously, and pi dot is same as force in this case. Anyway, the first term here, the Ri dot pi is basically mi Ri dot, and then therefore Ri dot is basically vi square. So this is mi vi square, which is 2t. So this first term means you're talking about twice the kinetic energy. T is the kinetic energy. So that's the story of the first term. Now let us go to the second term. Second term is pi dot Ri. So that's like Fi Ri. Pi dot is Fi, force. So then this dg dt is therefore 2t plus sum over I Fi Ri. Right? 2t came from this first term, this term, and this is just sum over Fi dot Ri. So therefore you have 2t plus Fi dot Ri. And now what you do is you take a time average of the left side, dg dt. Time average of dg dt is integral dg dt from 0 to tau, 1 upon tau. This part becomes a little bit on the delicate side of the calculation. Time average of dg dt. So that is this time average dg bar dt. And since you are integrating, the 2t will be replaced by 2t bar average. And this guy will also be replaced by the average because you can't be integrating this and not integrating that. You have to integrate everything. So everything, you get the time average. Now the argument is that if you make this tau go to infinity, whatever this is, it'll go away. So if you wait long enough until the system has reached a stable state, that for all practical purposes is tau going to infinity. So if this term goes away, then 2t bar plus sum over Fi dot Ri bar is equal to 0. But what that means is you have this inescapable contribution that t bar is minus 1/2 Fi dot Ri, or t bar is plus 1/2 gradient of a potential Vi dot Ri. Then the minus sign gets absorbed. So the virial theorem basically is this result. And it clearly establishes a relationship between the kinetic energy and the potential energy. Now, the simplest case of using virial theorem is suppose you have a one-dimensional system, so then it's just del V del R times R. And suppose you have a power law potential, like V equals AR to the n plus 1. Of course, n can be 0 also, but n plus 1. So now you see, if you apply the virial theorem to this, del V del R is n plus 1 times V. So T bar now is n plus 1 over 2 times V. This is time average, this is time average. Now this is a critically important result in physics, which is grossly underemphasized by us. I mean, if I wanted one lifeboat for doing many body calculations, this is my main lifeboat. Because I know how much of the system's energy is kinetic and how much is potential. If I could apply the virial theorem and do my due diligence. Problem is that applying the virial theorem for complicated potentials is not easy. You may not be able to do it analytically, but that doesn't prohibit you from doing it numerically. So numerically, you can always do it. This is, by the way, the reason why astrophysicists are so interested in it, because for them, measuring kinetic energy is not that difficult. And if they understand this relationship, that gives them a lot of information about the effective potential energy involved, part of which is surely gravitation. If there is some kind of dark matter or something sitting in there, vacuum energy, whatever it is, then that will show up. from virial theorem based observation plus analysis and simulations. Anyway, so this result you have to understand is very important because suppose is this n here is 1. If this n is 1, then clearly you can see that t is equal to v. And t will be equal to v. Furthermore, t plus v will be equal to total E. So therefore, t will be half of the total E, v will be half of the total E. Which means virial theorem tells you that if you take a harmonic potential, half the energy will be kinetic, half the energy will be potential. No way around it. And that's exactly what happens in a harmonic oscillator system. Half the energy is kinetic, half the energy is potential. Now let us try our luck with nonlinearity. Now suppose n is more than 1. If n is more than 1, what does it mean? It means t is more than v. Which means the slightest nonlinearity makes the kinetic energy exceed the potential energy, time average kinetic energy. So in all nonlinear systems, the kinetic energy is more than the potential energy. In other words, such systems are fundamentally different dynamically because they have always more kinetic energy than potential. So this is the message of the virial theorem. So hold your thoughts on the virial theorem. Now I'll tell you a little bit about equipartition theorem and what it means. So one of the things that happens is that there is a great need to understand these fluctuations. I told you these are very large fluctuations that happen in this quasi-equilibrium state, in this patchy grayscale state. Large fluctuations are happening. So one of the important things that one wants to know is how do we estimate these fluctuations? So it turns out there are some beautiful relations concerning fluctuations and specific heat and so on. Why is it beautiful? Because specific heat is a very equilibrium quantity. It can be calculated and measured. So if you can link a system's energy fluctuations to specific heat, then you know what equilibrium fluctuations to expect, ideally. Because specific heat is an equilibrium quantity. If you know the value, and if you can relate the specific heat value to kinetic energy fluctuation, which is what that Vmax T is, then you can check if your system is in equilibrium, or you can even ask the question that am I just reading too much into this? It's in equilibrium. Why are we fussing about it? Because specific heat is just as it should be. But then you can measure and see if specific heat is not just as it should be, you have not reached equilibrium. You're in a different state. So it turns out that we were measuring this fluctuation because in simulation you can measure it. How do we measure it? Well, we instantaneously measured the kinetic energy of the system, subtract from it the virial theorem generated kinetic energy, which is this quantity here, following the virial theorem I showed you. That measures the departure from the mean, and that therefore gives us a raw measure of the kinetic energy fluctuation. Of course, we time average and all that. We normalize it by dividing by kinetic energy, average kinetic energy, and etc. And then we actually track these fluctuations, the cumulative fluctuations, with this quantity called kappa up to a certain time point. So this is how we measure fluctuation. See if they're large, how large, because we have to get a handle on whether they're large or not. Actually, for Vivek, this kind of quantity is very important because although you may not be able to measure CV very well for a system, Hamiltonian system, but if you have a Hamiltonian system and if you can estimate CV with a simple model, your fluctuations can therefore be put in some category of this is the normal fluctuation and your market fluctuations may be very, very large. So something to keep in mind. All right, now I'll take you to the equipartition theorem. The equipartition theorem is by far a non-trivial theorem. And the general form of the equipartition theorem was introduced by Richard Chase Tolman of Caltech in the 1920s, I think 1921 or so. This paper is available. I have that paper. It's difficult to read, so I've tried to summarize it for you. And the box here, this text box, is actually what the Tolman equipartition theorem is. The equipartition theorem here is worked out in the microcanonical ensemble. So EVN system. QI is some generalized position coordinate. PI is a generalized momentum coordinate. So system, the conjugate momenta and position are involved. So QI, del E del QJ, and PI, del E del PJ. Equipartition theorem says that ensemble average, not time average, ensemble average of Qi del E del Qj and Pi del E del Pj equals Kt, Boltzmann constant times the temperature. This is the definition of temperature. And delta Ij. So I and J have to be the same. Now, if you take the Hertz system, general Hertz system, you have kinetic energy half mv squared, and then you have the Hertz potential. In Hertz potential, this is 5/2. We have left it in general as n. So now you can calculate, if I do V del E del V, so this is this guy, or overlap delta, del E del delta, then by applying the equipartition, sorry, the Tolman equipartition theorem, I can show that the kinetic energy of the system is half kT, and the potential energy of the system is 1 over small n kT. So in other words, if I know the energy, I can apply Tolman's theorem, and Tolman's theorem should tell me how much of the energy is kinetic, how much of the energy is potential, which is basically the virial result. Tolman's theorem also gives the virial result, right? Anyway, one can write in terms of temperature the following relationship, where this system energy is kinetic energy plus potential energy. According to potential energy, this is the way it can be expressed by Tolman's theorem, and this is the way the kinetic energy can be expressed in Tolman's theorem. So Tolman's theorem actually gives one very important layer of physics to our equipartition, sorry, our virial theorem. Virial theorem result does not bring in temperature here. It gives us the relationship. This guy, on the other hand, actually amplifies this relationship in terms of temperature while respecting Tolman's theorem. So these two are very important results, therefore. These two results are like two big lifeboats in your ship. So anyway, potential energy will always be 2 over n plus 2. Kinetic energy will always be n over n plus 2. This is what virial theorem therefore tells us, combining the two. And so, for example, if n is 2, you can see this is half, and n is 2, this is half. That limit checks out. Let's say n is 3. very nonlinear, n is 3, then it's 2 over 5, and this is 3 over 5. Kinetic energy is more than potential energy. If n is 4, like in the beta Fermi-Pascal-Olam-Singh, we have quartic potential, then 4 divided by 6 is 2/3, 2 divided by 6 is 1/3. 2/3 of the energy is kinetic, 1/3 of the energy is potential. When n goes to infinity, this number becomes 1. And when n goes to infinity, this number becomes 0. So in the limit of the hardcore potential energy goes to 0, kinetic energy becomes 1, as it should be. So virial theorem therefore beautifully checks out. All right, now let us go to the next step. I've told you about the Tolman theorem, equipartition. I've told you about connecting fluctuation and so on. Let's go here. I know the total energy because total energy I calculated here, remember? This total energy has been calculated. Okay, total energy has been calculated. So I can now do a del E del T. I can directly calculate CV of the system. And if I calculate the CV of the system, then in equilibrium, the CV will be n plus 2 over 2n times Boltzmann constant. So again, if n is equal to 4, let's say, as in beta Fermi-Pascal problem, here 4 plus 2 is 6, and this is 8, 6 over 8, 3/4. So, right, is that right? So n is 4, 4 plus 2 is 6, and 6 over 8 is 3 over 4. And CV value would be 3/4. 3/4 K Boltzmann. So now that you know CV, and now that you know sigma, it turns out, and you know Ke and all, it turns out there is a way to actually connect in equilibrium the sigma square, the kinetic energy fluctuation square to CV, and this is the connection, and this is another connection. Very important result. Simple result. Long known result, actually. So you actually have a measure of what is the normal kinetic energy fluctuation. And that is this quantity here. Of course, in equilibrium. Because remember, CV is being calculated in equilibrium. So it's all in equilibrium. So why am I taking you through all this exercise? I'm taking you through all this exercise because remember, at the end of the day, I am stuck on this plot. I know that there are wide fluctuations in this system. And I am desperately trying to get a handle on what this wide fluctuation is. And my guess of wide fluctuation is, of course, corroborated by this plot, where this patchy gray scale is there. How do I know how wide it is? So for that, I need to track the fluctuations and that brings us to what should be the fluctuation square. Of course, I can root it, and then I know the fluctuation sigma, like I've shown here. So now what happens is numerically, not experimentally, I can actually plot the fluctuation as a function of n. So it is sigma, the fluctuation, as a function of small n. This is small n here. And since I know sigma versus small n according to this formula, I can draw out how sigma versus small n should be. And as small n goes to infinity, sigma should go to 0. I can draw it out. And so I can also simulate that without using this result. And when I simulate that, actually this work was done by Michelle Zawosky. She was my PhD student from Canada. It turns out that the simulated points for two different systems. One is a 100 particle system and one is a 38 particle system, I think. For two different cases, they sit right on top of each other. So it turns out then that if we simulate the system, integrate the system long enough, or yes, simulate the system long enough, I actually recover a result which is consistent with equilibrium result, which means that this plot, if I wait long enough, will go to equilibrium. These fluctuations will indeed decay, although we don't see it. And this will indeed become a grayscale for this problem. So that should tell you why the system sizes here are so small, because we had to reduce the system size because we were looking at these simulations with more than 10 to the 10 collisions happening. That would take us long enough for the system to equilibrate. In fact, here we say 2 times 10 to the 7 at a minimum, but actually it's more than that. But basically, it's the same result. The CV also, the plotted CV from the formula and the simulated CV, they are very consistent. And I've been showing you results which are in microseconds and milliseconds. This result is in the order of seconds. So thousands of times more in time, deeper in time than otherwise. So this result actually is shown here. So it is a beautiful point then that we are able to actually achieve equilibrium in this problem. By the way, it's very rare. In no other system have we been able to achieve it. And of course, as I showed you, that Onorato paper, which mentions about the alpha Fermi Pascual problem going to equilibrium, they tried in a different way with collisions, with looking for important collisions and putting them in by hand and doing the calculations. Now, we are trying to tie all the laces together. So you know now that these fluctuations may change in time. The fact that they will change in time, I cannot say. They may change in time. There is a quasi-equilibrium phase where equipartition does not hold. And then there is an equilibrium phase where equipartition does hold that may or may not come in. This is one example where we see it coming in. But for example, the very messy Toda problem I showed you when I was starting class, we don't see any equilibrium there. What is the answer? Is there an equilibrium or no? I don't know. Mathematician would say no. So maybe it is a no, but we don't see it. We don't see it. If we wait long enough, I don't know what we should see. Everything is a surprise. Now let me take you back to one of the confusing things that I showed you. I showed you this plot where I said you have solitary wave, you have this solitary wave, acoustic wave type thing. The acoustic wave is also a nonlinear wave. I showed you that. I also showed you that Nesterenko's equations are a little bit of a problem for us. Why? Because we normally do them with direct simulations because they're difficult problems. Approximations should be done with great deal of understanding of what it means. And under no circumstances were we seeing Nesterenko's KdV solitron. We did see our strong solitary wave here. That solitary wave differs from Nesterenko's prediction. But the difference is very small. So okay, fine. We are happy to respectfully agree with each other. Here there is a problem. And that I told you that is a nagging pain. Why is that a problem? Well, how can we get around it? So I had one very, very brilliant student, a Japanese student, a long time back now, Yoichi Takato. And Yoichi was playing around with the Hertz problem. This was early on in his graduate career. Actually, he started this, I think, in his undergrad phase because he did 2 years of undergrad. He came from a mechanical engineering background, and he was actually the chief technical officer of a Japanese company that used to make simulation software. But he didn't know much physics. So here was this very erudite and educated and accomplished Japanese person in his early 30s or mid 30s who was an undergrad student for a couple of years before he started his PhD. Anyway, so this was done by Yoichi. This is the same problem, same system as we talked about, the equation of motion. Again, we are tracking the kinetic energy fluctuation. But what I had asked Yoichi to do, let me enlarge this a little bit. What I had asked Yoichi to do is to actually systematically study the fluctuations as one varies the delta. So the x-axis here is the axis which shows delta. It's in actual units of stainless steel for stainless steel balls. And these are the normalized fluctuations. Normalized fluctuations are these fluctuations where you are dividing out by the kinetic energy. So it's normalized to 1. I haven't shown the dividing out. Now, it was obvious that when the system had small delta, delta going to 0, the fluctuations would be large because that's where it's strongly nonlinear. We just talked about larger fluctuations here somewhere, I think. I didn't talk about, I didn't quite talk about it directly, but you see, when n goes to 2, that is Hertz, but when n goes to 1, that's harmonic. So if it's a harmonic system, you can see fluctuations are larger, and as small n goes up, fluctuations go down. No fluctuations for n goes to infinity. So therefore, the expectation was that as delta becomes large, it will go similar to n going to 2 because it's like a harmonic type problem. When delta is small, it's very nonlinear type problem. So I was telling Yoichi that, look, I mean, you should basically have high fluctuations at delta going to 0 and fluctuation going to 2. Fluctuation going down for harmonic systems. Normalized fluctuations going down. Now you have to be very careful in this problem because this fluctuation is for equilibrium timescale. And here as n goes to 1, it's slightly larger, but as n goes to 2 and so on, it's slightly smaller. But this is an equilibrium. But we are not getting to equilibrium. Okay, so I can't really compare this particular slide in toto with this particular slide. We know that the fluctuations are large because this system is in quasi-equilibrium for the most part. Anyway, this was our guess. And actually, Yoichi found that the guess was right. Indeed, you have larger fluctuations in the nonlinear system and smaller fluctuations in the linear system in quasi-equilibrium. Of course, when it goes to equilibrium, all of this will be different. But he found something very bizarre. You see, I said that he's increasing the load along the x-axis. So here, as he increases the load, first the fluctuations start to go down. And then suddenly, and very consistently for different particle sizes and conditions, You get this bump where the fluctuation goes back up. And then there is a precipitous fall to what is more or less equilibrium fluctuations. Sorry, harmonic fluctuations. And none of us believe this result. So Yoichi basically repeated this calculation a good many times. Good many times. More times than I would have done it, actually. And ultimately, he came to me and said, I'm very confused. I don't know what is going on, but I am absolutely sure there is no error. I can reproduce everything we know. So this must be real, but I don't know why. So I told Yoichi, look, fluctuations go up when you have a phase transition. In this problem, there is no real phase transition, but something funny must be going on. So we decided to image what is going on. And that brings me here. So if you actually make an image of what is going on over long time scales, here you can see time is measured in seconds in stainless steel, which is macroscopic time scale. And the first one is up to a tenth of a second. Second one is almost 7 seconds. That is huge. You actually have a soliton that keeps going back and forth and back and forth and back and forth and back and forth forever. The solitons is very slowly waning in strength. And this background scale is a very gray scale. Not patchy at all. It's almost like you have a harmonic, acoustic, or nearly acoustic background in which one soliton lives. It doesn't seem to scatter. And this was a mind-blowing result for us. It was like the system was indeed in a different phase. And soon it occurred to me that maybe, just maybe, Vitalis KdV solution that we never saw is what we were able to see. You see, the way Vitaly did his problem was he did not specify how large his loading delta was. This was easier to check because almost no delta, so very close to ours. So this regime turned out to be pretty much like this regime or a little less. This is the messy equation regime here. For this one. For this one, the wave actually looks sort of like this. But for the ones that we are seeing, the KdV, the wave actually kind of looks like that. And this is what gives that KdV solution. And we could even predict at what delta critical, we said, this will come because at this loading, the system's harmonic and nonlinear pieces, they begin to balance. They become competitive. And so Vitalis KdV solution is actually a solution when the loading and the bond compression, they are competitive. That ended up being the approximation one needed to be able to see that KdV limit. And indeed, I believe this is the KdV limit. I can't prove it because a soliton is a soliton. But it seems to have all the features that would make it into a KdV soliton. In fact, this work is pretty new. As you can see, this paper we just published in late 23. And this is that regime. So this is the case where Yoichi's results for uh, no loading apply with large fluctuations. In this case, kinetic energy is large. This is the regime where the kinetic energy goes to the harmonic kinetic energy. As you can see, it's 0.50 because the loading is large. But there is a sharp drop between the kinetic energy in the nonlinear regime and the kinetic energy in the linear regime. And that drop happens actually over about maybe about 2 decades in loading, because this is a log scale here. It's an amazing result. And in my opinion, this ties Vitali's experiments and our studies and actually deepens our understanding of the field. Beautiful. Okay. Now let me say a few things and I'll finish. I won't go any deeper in the system. But, remember I told you guys that here, I told you guys that there are fundamentally three solvable linear systems. Sine-Gordon, Korteweg-de Vries, and nonlinear or cubic Schrödinger. Korteweg-de Vries we have kind of touched upon quite a bit. So Sine-Gordon we didn't touch upon. Mostly used in field theory. Nonlinear Schrödinger equation is also used in field theory as well as in classical systems. So there is a classical nonlinear Schrödinger, a quantum nonlinear Schrödinger. So let me say a few words about this nonlinear Schrödinger equation without getting into inverse scattering and so on. I'll just sketch the nature of the solution. Basically, I've had this thing worked out by AI for me because it's very standard. But at the very least, you should know what it is, and you should know what is the relationship of the nonlinear Schrödinger equation with everything we have discussed in the various nonlinear problems like Alcee-Versus problem, Fermi-Pascal-Ulam problem, and so on and so forth. You should know the relationship. So this is actually the nonlinear Schrödinger equation. There's an imaginary part, del psi del t is equal to minus half del x del 2 psi del x2 plus k psi mod square psi. It's a cubic term here. That's my cubic nonlinear Schrödinger equation. And then you have a time-dependent first order term here. Often not given, but it is very, very interesting to note that psi is a complex field. It's not a real field. And this equation, which is a continuum equation, can be generated by the following continuum Hamiltonian. So this clearly is one piece of it, and then there's a quartic piece of it. Now, what is extremely interesting here is this Hamiltonian, if you look at it from a distance, hold the thought, don't let it go. It's very similar to this Hamiltonian, right? So our problem of cantilevers that we discussed, which was experiments of Alcee-Versus, is very, very similar to the nonlinear Schrödinger equation problem in the continuum version. And we know what Alcee-Versus problem gave us. Alcee-Versus problem gave us localized excitations. So what should this guy give us? It should give us localized excitations. Maybe some solitons also, the moving bunches of energy. but localized excitations. Now, if the commutation relationship between the size is described using Poisson brackets, then you are dealing with the classical nonlinear Schrodinger equation. And if it is described by the square brackets, the uh, commutator brackets, here I say the same thing, by the commutator brackets, then it becomes a quantum nonlinear Schrodinger equation. Now, this part is interesting. The case with negative k. What is k? K is right here, kappa actually. So if kappa is negative, they generate, the problem ends up with some kind of localized excitations, which are called bright soliton solutions. That is for kappa negative. But if kappa is positive, then you get slightly different property. They're called dark soliton solutions. By the way, this nonlinear Schrodinger equation is also very useful in describing the dynamics of Bose-Einstein condensates. This nonlinear Schrodinger equation is very widely used for a lot of different phenomena. People have described very large rogue wave type water waves uh, using this nonlinear Schrodinger equation approach. They are called peregrine solitons. I'll write it out. Basically, large fluctuation solutions. This is these solutions are relatively recent, maybe about 25 years old, 30 years old. They are basically, medium is fine, and then suddenly this large wave comes and stabilizes there. That's not how a rogue wave is, but it's sort of similar to a rogue wave. If it moves, then it's like a rogue. I don't like that wave in particular because we can generate better rogue waves, but it's a very well-regarded area of research. This problem was actually analytically solved, and this was this famous work of Zakharov and Shabat. Anyway, this is the quantum version. Same problem. And this also has been solved by Elliott Lieb and Liniger. And the thermodynamics of the system was done by Yang, same as Yang, Li, Yang. So anyway, so the point, the reason why I'm saying this to you is to give you the sense that there are many ways of looking at these problems, and it doesn't matter what your background is. If you are very comfortable with the analytic mathematical background used in continuum systems, you can use the known equations. Then you can use the versions of the known equations that can still be solved with minor changes here and there. So that's why I didn't name them, but there are lots of equations, at least 15, 20 of them, which are basically cousins of these three equations that you can also solve using the same kind of approaches like inverse scattering and so on. And that is the field that applied mathematicians study, those who look at dynamical systems. I didn't come with a formal background in solitons and so on, because you don't learn that in physics courses. But I fell into this field because I got interested in stuff, and one thing led to another, and I came here. And when I came here, I was trying to teach myself, and that led me to pick the Hertz problem, which was least explored, because that would be most fun, I thought. And that led me to many beautiful results. And that also led me to help my friends who are in applied mathematics, because I could tell them, look, guys, this is what we see. Do you see that? Oh, we don't see that. How did you get that? So there's a very healthy collaboration I have with my applied mathematician friends from all over the US, pretty much, and beyond US also. Now, again, I've given you some literature on the nonlinear Schrodinger equation. And essentially, this is the version that is used for the Bose-Einstein condensate. And as I said, kappa greater than 0 in that case is used. Focusing case, they say, various names. So let me close with that. The reason why I didn't want to do the nonlinear Schrodinger is because the nonlinear Schrodinger is a little bit more difficult, more rich than the KDV. But the problem can be tackled. The problem can be solved, as done by Zakharov and Shabbat. Uh, People have tried to do, basically separate the variables out, space and time, and try to solve this problem. I didn't take you there because it's not really necessary. You can look it up if you have. But I just wanted to give you a basic core idea of how this thing works and why it is relevant. Because the quadratic plus quartic potential problem is basically a double well problem or a steep well problem. And the double well problem and the steep well problem is widely used in physics. For example, in phase transitions, it's used. In cosmology, it is used as the scalar field of the universe rolls over, leading to exponential expansion, which is inflation. So it's widely used. I mean, you name it, you see it all over physics. Landau theory is based upon it. All of these ideas are tied to what also ties in with the nonlinear Schrodinger equation, Ginzburg-Landau equation, all of that. But this just gives you the physics intuition, I hope, such that if at any point you want to educate yourself on studying nonlinear dynamical equations, math departments have excellent courses that go deep into the structure of how to construct the solutions. And that has its own, advantages. I have a very physicist viewpoint. I have quote unquote, mathematicians would say the engineer's viewpoint. Although my engineering is different from Vitali's engineering. All right, let's close. So we are meeting on, I think, is it the Tuesday meeting next, or we had discussed a meeting on Saturday or something? What was that
Yeah,
about?
Saturday.
What was that
You
about?
you were gonna ask us
About
questions about the course?
Oh, that was Saturday, and then Tuesday is the presentation.
Yep.
Okay. All right. I'm
yeah.
going to set up. So what you do is just go over. I'm going to send this whole slide deck. Uh, well, I don't know if I can send the whole slide deck without crashing systems. Can you guys tell me how far along I sent you? Because I have also gone
You
back.
can do one thing. You can upload it in your drive and then share the drive link.
I don't have a drive, and you won't be able to get into the box drive that UB uses. Um,
Let me
so,
check. Uh,
I mean, I have iCloud, but I
I
have
have
only
one that's 248 slides.
248. Oh, that was a long time ago.
Mhm.
Um,
I don't know if that's my most recent, but that looks like it's my biggest, so I've maybe chopped the other ones up.
okay. So
You have
248. Tell me.
also sent until this Korteweg-de equation problem with that photo of 1895.
This one,
Yeah,
299.
this 299. Yeah.
Okay. Okay. And the one that Tony was saying is two. What did you say? Two?
245.
Uh, Actually, I've also gone back and changed some of these. So maybe I should just start
Yeah.
from.
Yeah.
I've ch-
Because the recent 42 slides that you have sent does not have that your waves and yeah.
yeah, I've deleted some things also and added new stuff. So what I'm going to do, let me see where I can load it up. Can you guys
Yeah.
access iCloud?
Oh,
No? Uh, okay, let me see. I can try iCloud. I can try my Google Drive maybe. Uh, one Google account, I have extra space, so I can load it up. Then you can just download it from the Google Drive. Maybe I'll do
Yeah.
that. Okay, let's do that. All right.
How
So
big is the file?
I'll tell you. It's quite big actually. Because it has a lot of pictures, so 140 megabytes.
So WhatsApp me then. WhatsApp is easier.
Tony, you have WhatsApp?
You should have, I guess.
You have WhatsApp? Okay, send me a. Can you send me a WhatsApp? You know my number? You know my number.
I do not know your number.
Oh, 716-907-4961. Let me try WhatsApping Tony right now.
Yeah,
716
140 MB.
716-907-4961.
4961.
Yeah, 907-4961.
Alright.
Oops, how come this is not going away? Yes.
All right, I just messaged you.
Yes, fantastic. So let me try and see if I can put this document. Um, It looks like it went, Tony. Let me try Vivek.
I got it. Yeah, I got it.
You got it. Amazing. It was a brilliant idea to try WhatsApp. WhatsApp is very versatile. I actually use it a lot.
Yeah, I got it.
You got it? See if you can download it fully. I'm done.
Yes,
Okay.
it is in the process.
Okay. Tony, you can download, right?
I'm just emailing it to myself right now.
Yeah, it may not be good to download on a phone. So now there is the whole thing I've sent. So therefore you have every possible slide that I have made. I've cleaned up some of the older slides.
Yep, I can see it entirely. It's here. Downloaded it.
Okay. All right. All right. I better run because I need to go to the talk today. So I have to go up to the
Yes.
department. So, all right. See you on Saturday afternoon.
Yeah.
Yeah.
Bye-bye.